Hello, I hope you can all hear me. Welcome to the this walkthrough of the P1P2P3 higher paper from this time last year in advance of tomorrow's exam for physics. So I'm going to walk through each of the questions and at the end I'll have a few minutes I'll put aside to allow you to ask questions in the chat box. If you can ask questions throughout in the chat box, I'll try and look back every now and again and answer those. First thing you'll come to when you open up the formula book exam page is the formula sheet here, which has each of the formula lists divided into sections. The first one here, the Earth and the Universe, that one is P1. There is no formula sheet for P2. P3 is sustainable energy, and then we come on to the stuff for the additional exam, which you'll do after half term. That would be P4, explaining motion, P5, electric circuits, and P6, radioactive materials. Okay, on we go then. So question number one, this has become quite an infamous question. It's a bit nasty for the very first question in an exam paper. OCR do seem to like to start with 6-mark questions. This is a 6-mark question for P1. And it begins by saying that observations of the star Tau Ceti have shown that it's very similar to our sun, surrounded by a cloud of dust, has several planets, and that 5 of those planets are at least as big as our sun. Now, students who don't know the spec inside out will look at this question and they'll see the words Tau Ceti and they'll go, I have no idea what that is. Maybe I've just not revised it. Let's skip this question. Those who know the spec inside out will know that they're not supposed to know anything about Tau Ceti. I've never heard of it before. The point here is that it tells us straight away that Tau Ceti is very similar to our sun. In other words, it's asking a question about our sun and the solar system around it. Once you start to look at it like that, it's actually a very straightforward question. It's asking us to draw a labeled sketch of the Tau Ceti system. In other words, to draw a labeled sketch of our solar system, showing how the different parts move, and describe how these different parts may have formed. So to begin with, we need to sketch the solar system. So in the center of the solar system, we have a sun. Okay, that could be our sun. In the case of Tau Ceti, it's Tau Ceti itself, the star. And it tells us that there are at least 5 big planets orbiting. So we need to use 5 planets. Put one there, put one here, put them all wherever we want in separate orbits around the sun, and we need to draw those orbits on. I'm doing it very roughly here. You'd hopefully be a better sketcher than me. These orbits should be virtually circular. Make sure that each planet has its own clear orbit, that it's not overlapping with another one. And one last one. What a terrible sketch I've done here freehand. But there we have the sun with, make it really clear that these are planets orbiting around it. So that is our labeled sketch of the Tau Ceti system. It's showing how the different parts move as well. So we've definitely got a few marks for that. Now let's think about what we need to write below. It says we need to describe how the different parts may have formed. By the way, this is a question that was aimed, you don't know this from the question itself, but from the mark scheme it tells you that this question was aimed at students up to a grade C. So in every OCR exam paper, higher tier paper, there will be 3 6-mark questions. A star, one of them is usually aimed at sort of grade A, and the other one will be aimed at grade C. So somebody getting 6 marks in this question would probably be on about a grade C to grade B. So it shouldn't be difficult to get the 6 marks here, and actually it doesn't require very much to get that. This is, remember, a P1 question, not a P7 question, so you don't need a lot of detail. The cloud of dust and gas. So we start with a cloud of dust and gas in space. That comes together via gravity, attracts it all together. At the middle part forms the star and starts to fuse, starts to undergo nuclear fusion. And the leftover bits on the outside form planets. Now, actually, that's more than we need for the 6 marks. We've got our labeled diagram, and we've given a little bit of detail already. So probably 2 of those statements will be enough to get the 6 marks here. So as I say, not a lot for 6 marks, but the key here is to understand that it's not a trick. It's asking us to talk about our solar system. Question 2 is about earthquakes. It gives us a data table, and it can produce tsunamis. So with the table here, it tells the depth of water, the speed of a tsunami, and the wavelength of that tsunami wave. So the tsunami crosses a tsunami across the Indian Ocean from the earthquake on the coast of Indonesia to Africa. It took 8 hours and 20 minutes, and the speed of the tsunami was 180 meters per second. Calculate the distance in kilometers from the Indonesian earthquake to Africa. Well, we've got a speed. Now, you should know from key stage 3 that the equation for relating speed, distance, and time, but actually specifically related to waves. It's given to us here in the P1 formula sheet. Distance equals wave speed times time. We know that the speed is 180 meters per second, and we know that the time is 8 hours and 20 minutes. However, we must be consistent in our units here. So the must be in meters, the speed in meters per second, and therefore the time needs to be in seconds. So let's get our time into seconds. 8 hours is times it by 60 to get into minutes, and by 60 again to get into seconds. And to that we need to add 20 minutes, which is 20 into seconds. And that gives us a time of 30,000 seconds. So then our distance in meters will be 180 multiplied by 30,000, which gives us 5,400,000 meters. And it tells us, of course, that we want our distance in kilometers. It's very clear about that in the question, so don't forget to convert that to kilometers. So divide it by 1,000. That will be 5,400 kilometers. Part 2 says estimate the depth of the Indian Ocean, which you can assume to be the same at all parts. So here it's worth looking at our table. The depth of water compares it to the speed and the wavelength. We don't know the wavelength, but we do know the speed of the wave. We know the speed of the wave is 180 meters per second. That would place it somewhere in here, somewhere between 140 and 200. which means that the depth of the water must be somewhere between 2,000 and 4,000. So it doesn't matter too much what we choose here. I'm going to put 3,000 meters. The mark actually here isn't for saying 3,000 meters. The mark is for the explanation. What I'm going to say is using the table 180 meters per second means that the depth must be between 2,000 meters. That would be enough to get you the mark there. Part B, it's been suggested that the speed of a tsunami is directly proportional to the depth of the water. Explain what directly proportional means and use the data in this table to see if it's true. When this exam was done as a PPE, as a mock exam by students, hardly anyone got this right. It's really directly proportional is not the same as just saying there is a correlation. It doesn't just mean as one increases, the other increases. That's not the case. Directly proportional means that if you divide one number by the other, in this case we can divide speed by depth, or we could do it the other way around, it doesn't matter too much. Divide speed by depth, it will produce a constant. So for any pair of values, so one speed and one depth, dividing one by the other should give us the same number every time. And we can test that by doing 45 divided by 200, which gives us 0. And try it with the other pair of values here. We have 10 divided by 10, which is obviously 1. Those two do not equal each other, so it is not true. There is not a directly proportional relationship between speed and depth. And part C shows the tsunami wave in mid-ocean, and again near the land you'll see that the amplitude of the waves has increased, but actually the volume of water within each of these peaks has remained the same. So we need to explain why a tsunami might not be noticed by a ship in mid-ocean, but can cause terrible damage when it strikes the land. Well, you'll notice that near the land it has a bigger amplitude, which means the wave is taller. There's a couple of reasons why that could cause additional damage. It could get taller waves can get over obstacles or move further inland. Also, taller waves will have more potential energy. If you think about it, this is a bit of P4, I suppose, but even though there's the same amount of water in each wave here, the water in the taller wave will have more potential energy. So that potential energy at the top of the wave will come crashing down on people and on homes. So it causes a lot more damage. So a taller wave is more dangerous. On to question 3, the very common to have questions about Alfred Wegener's theory of continental drift. Many scientists didn't accept his theory when it was first proposed. These were the scientific observations that were available in 1912 when he proposed the theory. So we've got to say which ones support his observations, which ones contradict it. So fossils of tropical plants are found near the South Pole. What that means is that plants that could only grow in tropical areas, the remains of those have been found at the South Pole, where obviously tropical plants couldn't grow. So clearly these plants haven't grown there and then died and fossilized at the South Pole. They must have they must have died on another continent, and then the continent itself has moved down to the South Pole. In other words, what we're saying here is that the South Pole, Antarctica, didn't used to be at the bottom of the Earth. It used to be in a tropical region. That definitely supports Wegener's theory of continental drift. Humans are found on all continents. Well, that's not necessarily true. Humans can cross oceans, so it doesn't contradict Wegener. It doesn't support Wegener. So we can take the third column here to say that it doesn't contribute. South America and Africa are separated by the Atlantic Ocean, but both have sedimentary rocks. Well, sedimentary rocks are just formed by sediments being compressed. There's no reason why they necessarily have formed at the same place. They've just, so again, that doesn't support or contradict. And the width of the Atlantic Ocean is not changing. Subsequently, we have discovered that's not true, but in 1912, there was no evidence that the Atlantic Ocean was changing its width, so that contradicted Wegener. Wegener said that the continents were drifting apart, and they clearly aren't. The next part is about the magnetic stripes. So here we've got a diagram that have been found on the seafloor in the middle of the Atlantic Ocean. The darker areas here representing the rocks that are magnetized in one direction. The lighter rocks represent the rocks magnetized in the opposite direction. This is quite a complex part of P1 to understand. It doesn't come up in the foundation paper, but in the higher paper, you need to understand that as seafloor spreading takes place, new molten rock is coming out from the seafloor, and then it's setting as rock. Now, that rock contains tiny bits of iron which become magnetized according to the direction of the Earth's magnetic field. Now, what's a challenging point to understand here is that the Earth's magnetic field doesn't stay the same every maybe 500,000 years or so. It changes direction, which means that any rock formed after a direction change will be pointing in a different direction. So this can be used as evidence that over time the continents have drifted apart. So here we have a tick box to identify the which of these 4 facts are the best explanation. They're all correct, it says. So it's not asking which are correct, it's asking which ones are the best explanation. So it's a nice exercise actually in understanding relevance of questions, which is very important when you're attempting a 6-mark question especially. So the Earth's crust lies on top of the mantle. Yes, it's true, but does it explain what we're talking about here? The Earth's magnetism changes direction about every 1,000,000 years. That's definitely a helpful explanation. Give that a tick. The thickness of the seafloor increases as it moves away from the middle. Again, not really relevant to our explanation, and the seafloor spreads out from the center. That does help our explanation. On to question 4, which is a very short little question. It's just the last part of P1. Which one of these elements is used to produce energy in the sun? We've got hydrogen, helium, carbon, oxygen, and iron. Well, it is hydrogen fusion that takes place inside stars to produce energy. In larger stars, helium fuses, but in our sun, which is a middle-aged star, this is sort of P7 knowledge, I suppose, it is hydrogen that fuses. Which 3 of those elements must have been made inside stars? Well, hydrogen and helium have existed in the universe since the Big Bang, but only the heavier elements, carbon, oxygen, iron, and anything heavier than these have to have been formed in a star through nuclear fusion by combining together hydrogen, helium, and so on. So it is these 3: carbon, oxygen, and iron. And that's the end of the P1 section. I'm just going to have a quick look at the comments to see whether there's any comments I can help answer. Okay, there's been a request to repeat question 4b. Nuclear fusion combines elements together the only place in the universe that nuclear fusion takes place is in stars, or actually inside a laboratory near Oxfordshire. It doesn't occur in anywhere else but stars, so you cannot explain the existence of carbon, oxygen, iron, or any other element that's heavier than helium, in fact, through any process other than nuclear fusion. They have to have been formed by combining together hydrogen and helium. Therefore, those three elements have to have been formed inside stars. Hydrogen is the simplest element. It's one proton, one electron. That has existed since the Big Bang. In fact, almost everything that was formed from the Big Bang was hydrogen, and also some helium. So those two elements did not necessarily form inside stars, but the carbon, oxygen, and iron have to have formed inside stars. The reason those elements are available on the Earth now and in our bodies, when we're largely made of carbon, the reason that is the case is because we are made out of bits of old star. A star must have exploded previously in this part of the universe, and our sun and our planet and ourselves are formed out of the leftover dust from that planet. So we are stardust in that sense. So all heavy elements, heavier than helium, must have been formed inside a star through nuclear fusion. Look at question number 5. We've got a graph showing how the average temperature of the Earth and the concentration of carbon dioxide in the atmosphere have changed over the last 300 years. So each point here is marked with the year the readings were taken place. So you can see that the carbon dioxide concentration going from 1700, 1750, 1800, 1850, 1900, it didn't change very much around the first couple of hundred years there, and then in the 20th century it did increase, and then again, and also the average temperature increasing over that time, but much more dramatically in the period when the carbon dioxide has been increasing. We've then got 5 statements from 5 different people, and we need to consider which of these statements first of all, which of these statements are describing the data. Remember, the key word here, describing, is just saying what you can see, not coming up with a reason for it, just saying what you can see. So Alice is saying there's a positive correlation between temperature and carbon dioxide concentration. So that she's describing what she can see on the graph. So Alice is certainly one of ours. So I'll put a D for describing next to her. Burning fossil fuels increases the carbon dioxide concentration. Well, that's not something you can directly read from the graph. That's an explanation for what you can read on the graph. So we'll put an E for explanation there. Chandra says that carbon dioxide concentration didn't change much until after 1900. Again, he's just describing what he can see on the graph. Deborah says she's worried about the effects of global warming on the environment. She's neither describing the graph nor explaining what she can see on the graph. She's just making a related statement. So she's doing neither. And Eddie says that carbon dioxide is a greenhouse gas. It makes the Earth absorb more of the sun's radiation. Again, that is an explanation for what we can see. So if you scroll down here, we're looking for 2 descriptions. So that's Alice and Chandra. And the 2 explanations would be Ben and Eddie. Graph opposite and similar data produced by other scientists raise concerns about climate change. One such concern is that low-lying land could be flooded. State and explain 2 other changes that could result from global warming. So be careful. A lot of students tend to write for this question that that flooding could occur. Well, that's given to you in the question is looking for other things apart from flooding. So one thing you can suggest, actually, the marks here, there are 3 marks. You should identify 2 changes, and you need to explain at least one of them. I'm going to identify 2 and explain both of them, actually, which is slightly beyond what's needed. So habitat change is one of them. So plants and animals could find that their habitats have changed, have moved because they've become too hot or too cold. A second explanation here, a second change, or extreme weather, more hurricanes, etc. And this could be because there's more water in the atmosphere. Now remember, the marks, you get 1 mark for, so you get 2 marks for identifying 2 changes and 1 mark for explaining one of them. So actually just saying habitat change because it's become too hot or too cold would get you 2 marks, and then saying more extreme weather would get you the 3rd mark. P2 is a strange unit, really. It kind of meanders around the topic of radiation quite a lot. So you need to know in depth the electromagnetic spectrum, which radiations are ionizing, which radiations are non-ionizing. You need to know how frequency and energy change as you go across the electromagnetic spectrum from radio waves up to gamma waves. And then on top of that, you need to know the global warming, climate change, greenhouse effect stuff, and also the section to do with digital and analog signals. And that's what part 6 is about, question 6. So question 6 asks us to write down 2 advantages of using digital signals. But the main advantage, this came up actually as a 6-mark question, I think in 2014. Much more difficult to get the marks for, obviously, than this 2-mark question. So write down 2 advantages of using digital signals. Well, it is easier to remove noise from digital signals. So when a digital signal, if I just do a quick sketch here, an analog signal and a digital signal. When an analog signal picks up noise, it looks like this. When a digital signal picks up noise, it looks like this. Now, because you know that a digital signal can only either be 0 or 1, it's very easy to reconstruct this pattern, even though you've got this noise. However, the analog signal can have any value along this wiggly line, which means it's very difficult to work out exactly what the precise line should be. That's why it's easier to remove noise from a digital signal than an analog signal. The second one, there is a couple of things you can say here. You can either say they can be stored in computers or they can be processed by computers, anything like that, which you can't do with analog. If you want an analog signal in a computer, you have to convert it to a digital signal first. Part B says both analog and digital signals can be sent through the atmosphere or along optical fibers. We've got some statements below about those 2 different ways of sending a signal. Some of them are true for both. Some of them are true for one, and some for the other. Okay, so it tells us that the first one, the signals can be digital or analog. Well, the question actually tells us that it's true for sending signals through the atmosphere. So, for example, beaming them for television or as radio waves or microwaves and mobile phones or up to satellites. Along optical fibers, that's the kind of thing that's used for broadband internet or cable television. So microwaves can carry the signal. Well, that's certainly true for sending through the atmosphere. That's how mobile phones work and how satellite television works. But you cannot use optical fibers for that. Optical fibers tend to just be used for visible light, not microwaves. Not much of the signal is absorbed by the material it passes through. Well, it's definitely true for passing through the atmosphere and also for optical fibers. If it wasn't true, you wouldn't get very far. These signals would run out so quickly that it wouldn't be worth doing. The signal uses photons of less energy than X-ray photons. Or X-ray are, with the exception of gamma, they are the second most energetic type of electromagnetic radiation. You definitely don't want to be using X-rays or gamma rays or anything that energetic because they're harmful radiation, and so you wouldn't be beaming through the atmosphere. So that's it's true. It uses photons of less energy, usually radio waves or microwaves for atmosphere, and visible light for optical fibers. Travel at a speed of hundreds of thousands of kilometers each second. Yep. Even though they slow down slightly when they're moving through optical fibers, they are still close to the speed of light, which is 300,000 kilometers per second. And onto the 6-mark question for mobile phones. sorry, for P2, which is about mobile phones. It's don't believe all these scares about mobile phones. Their power output is less than 1 watt. A kettle is 2,000 times more powerful. Mobile phones can help to keep children safe. The UK Chief Medical Officer strongly advised that children and young people should be encouraged to use mobile phones for essential purposes only and to keep all calls short. Explain the risks and benefits of allowing children to use mobile phones. And it says explain here, so it's not enough just to write down a risk and a benefit. We need to actually explain those. So let's begin with a benefit. Now, there are lots of benefits you can write down here. Pretty much anything that's sensible would get you the mark. For example, children can contact their parents in an emergency. So that's a benefit of children having mobile phones. A risk is that mobile phones are used close to the head, and young people have developing brains and thinner skulls. Now that's an important point. Is to bring this not just about the general risks attached to mobile phones, but also specifically for young people. The brains of young people are developing; they might be more vulnerable, and that the skulls of young people are thinner, which means that it might be more likely that any damaging radiation would get through to them. So if you're looking for 6 marks in this question, which would be an A or an A star answer, you need to be referencing the differences with young people. However, at the moment, we haven't really been scientific enough. We haven't talked about what damage could be happening. So we should acknowledge that microwaves, which is what mobile phones use, are non-ionizing radiation. So it is unlikely to cause cancer. However, microwaves heat up water. They do this by exciting the water molecules because they make the water vibrate. So could heat up the brain, which remember has a lot of water in. Or cook it. So that's the hazard really. So how do we explain the risks and benefits? Yes, we've given a benefit there, quite a flippant one, but it's fine. We've come up with a risk, which is that mobile phones could cook the brains of young people. We've explained that in terms of the additional risks attached to young people because their brains are developing and their skulls are thinner. We've acknowledged that it's non-ionizing radiation, so it's not going to cause cancer, probably. But it could heat up the water. It could damage the brain in some way as a result of that. Okay, that brings to an end P2. So let's just have a quick look at the comments, see if there's anything. Yeah, just to respond to one question there. This video is streaming live, but it'll automatically be uploaded immediately afterwards, so you can watch it back at your leisure, jump between questions and so on. Okay, and on to question number 8, the first part of P3. It says that a solar farm is being planned for West Wales. The data for this project are given below. Now, this is interesting because actually it's not asking you to really use any of the equations for P3. It's giving you a lot of information, and you should be able to, kind of using almost common sense and some logic, work out how those equations go together. So it tells us how much radiation, so that's how much energy is coming from the sun, that will actually hit these solar panels. And it says for every square meter of panel, 0.9 kilowatts will be coming from the sun. It tells us how many solar panels we've got. It tells us what the area of each solar panel is. And finally, the efficiency of those solar panels. So how much of the sun's light will be converted to electricity. Planners say the farm will produce 7.5 megawatts. We need to use the data to check if that's true. Obviously, we need to reach some conclusion at the end. So the first thing to do here is to work out what the total area of solar panels for the farm will be. And from that, we can then work out how much energy is coming in, and therefore how much energy is coming out using the efficiency. So we know there are 35,000 panels, and we know that each panel is 1.2 meters squared. So that gives us a total area, by multiplying those two numbers together, of 42,000 meters squared. We know that the intensity of the radiation panels, so how much radiation we have, how much power from the sun, is 0.9 kilowatts per square meter. So to work out the total input power, that's the power from the sun, we need to multiply 0.9, that's the kilowatts per square meter, by the number of square meters, which is 42,000, which gives us 37,800 kilowatts. So if you'd done those two stages, I think you'd be on 2 marks, or perhaps not, perhaps that's 1 mark so far. And then to work out the output power, we could look back at the equation for efficiency here, but actually just use a bit of common sense. Remember that 15%, if you're doing any calculations with it, put it as a decimal, which is 0. The output power is obviously going to be less than the input power. The solar panels cannot create energy, so some of it's going to be lost. So the output power is going to be our input power, which is 37,800, multiplied by 0.15, because that will give us a smaller number. If common sense told us that a bigger number was needed, then perhaps dividing by 0.15 would be necessary. But here we're multiplying 5,670 kilowatts. So that would get us 2 marks. Now the question says we need to compare that to 7.5 megawatts. So it's important that we convert that into megawatts so we can do a suitable comparison. So that can just divide it by 1,000. That comes to 5.67 megawatts. And actually, that would probably be enough for 3 marks, but just for completeness here, that is less than 7.5 megawatts. So the project planners are incorrect. On to question 9. Now this question gives us a few calculations to do, and it will require using the formula sheet. The first one, a kettle is plugged into a main socket. It draws a current of 12 amps. We need to know the power in kilowatts. So let's take a look at our formula sheet to see what equations have current and power. So we're looking for the P3 formula sheet. Sustainable energy here, and we have this equation: power equals voltage times current. Now, in that we've been given the current, we need to find the power, but we haven't been given the voltage. Well, the reason for that is because you are expected to know what the mains voltage is, and the mains voltage in the UK is 230 volts. So that's just a bit of information that you have to know for this exam. So we said that power equals current times voltage. So current here is 12 amps. Voltage is 230. And that gives us an answer of 2,760 watts. Now, a lot of students got this calculation correct, but then circled the wrong value because they went for the 3,000 value here because that's close to 2,760. However, notice that the question asks for the power to be given in kilowatts, not in watts. So that will be 2.76, which means the closest value there is 3. The second part B, says it takes 4,200 joules to raise the temperature of a litre of water by 1 degree. How much energy is needed to heat up a litre of water from 20 to 100 degrees? Put a ring around the correct value. Now, this one doesn't require any formulas from the formula sheet. It just requires a little bit of logic. If it takes 4,200 joules to raise the temperature of water by 1 degree, how much it's going to take to get it from 20 to 100? Now, that is a difference of 100 minus 20. That is a difference of 80 degrees C. So if it takes 4,200 to raise it by 1 degree, we need to multiply that by 80 to work out how much it will take to raise it by 80 degrees. So 4,200 times 80 equals 336,000 joules. And it's just saying to one significant figure which one is closest. So you would round that one to 300,000 joules. Finally, a camping kettle is marked 12 volts, 170 watts. It needs 70 kilojoules to boil the water in it. How long will it take? So we've been given a voltage, a power, and an energy. But joules is energy, watts is power. And it's asking us for how long. So we're looking for a time. So we know power, energy. We're looking for time. And they've also given us a voltage. Now, we don't need all of those things. If we look back at the formula sheet again, it tells us that energy transferred equals power times time. It doesn't have a voltage in there. So that's a bit of a red herring for us. They've thrown it in just to throw us. Energy transferred equals power times time. Energy equals power times time. So we'd rearrange that to get time equals energy divided by power. So the energy here is 70 kilojoules. Remember, that's kilojoules, so we need to convert that into joules. So that's 70,000 joules divided by the power, which is 170 watts. And that would give us 411.8. Now, that doesn't match. The only one that we've got in seconds there is 0.4, and that's nowhere near. So we need to convert this into minutes to find out. 411.8 divided by 60 to convert minutes to seconds. Sorry, seconds to minutes. And that will give us 6.86. So the nearest value there, obviously, is 7 minutes. Question 10 shows us a generator. This is something that will be covered in a lot more detail in P5, but for P3, you need to know the basics. Which one of these combinations would certainly raise the voltage generated? Using a weaker magnet, rotating the coil faster. Well, rotating the coil faster would increase the voltage, but using the weaker magnet would have the opposite effect. So we don't know whether that'll definitely increase the voltage. Stronger magnet and rotating the coil faster. Yes. Both of those things will contribute to a larger voltage. Check the other ones. A weaker magnet rotating the coil slower. That will definitely reduce the voltage. And a stronger magnet and a slower rotation. Again, one could cancel out the other. We don't know for sure if that will increase the voltage. Part B is a very, very common question in some form. You need to be able to use this kind of block diagram for power stations. In this case, it's a hydroelectric power station. If this was a coal or nuclear power station, a fossil fuel or nuclear power station, this first box here could be a boiler. But in this case, it's not. It's falling water because it's a hydroelectric power station. So the first stage here, the falling water turns a turbine. Okay, or again, if this was a fossil fuel power station or a nuclear power station, the turbine would be turned by the steam produced by the boiler. Now, the job of that turbine is that it turns the generator, and that will generate the electricity. Now, the electricity that's produced is relatively low voltage. That voltage needs to be stepped up to a higher voltage so that the current is lower and less energy is going to be lost across the national grid. So to do that, we use a transformer. So those are the stages you need to learn. Boiler, if it's a coal or oil or gas or nuclear power station. But these three in the middle are always there: turbine, generator, transformer. Even if this is a wind turbine, the wind would turn the turbine, power the generator into the transformer. Another numeracy question here for part C. There's been quite a few calculations in this paper. So it says the Three Gorges hydroelectric dam in China generates 2.25 times 10 to the 10 watts. We're going to handle some standard form here. Make sure you know how to do this on your calculator first. There is a button that makes things easier. It usually says it will either say EXP on it, or more commonly on newer calculators, it will say times 10 to the X on it. Use that button rather than trying to do it the long way. Otherwise, you'll end up with some problems when you multiply and divide and things. So if you're not sure how to do that, check with someone first. So it uses 2.25 times 10 to the 10. So it generates that much, but it uses 1 times 10 to the 8 watts just to power the actual dam itself, to run the lights and so on. The national consumption of China is 3.2 times 10 to the 12 watts. So you need to calculate what percentage of all of China's electricity is provided by that dam. So the first thing we need to do is subtract the dam from the power that's generated by the dam, because that's power that's not going to be fed back into China. So the output is equal to 2.25 times 10 to the power of 10 minus 1 times 10 to the power of 8. And you'll see there, because 1 times 10 to the 8 is around 100 times smaller than, it's actually around 200 times smaller than 10 to the power of 10, it barely changes the initial answer. That comes out as 2.24 times 10 to the 10 watts. We then need to find out what fraction of the China's electricity consumption is provided by that. So to do that, we divide the output times 10 to the 10 by the total consumption of China, which is 3.2 times 10 to the 12. And that will give us 0.007. Now that's a fraction, it's not a percentage. So we multiply that by 100. And that will give us 0.7%. I was marking this as a mock paper, that some students saw 0.7 and then decided to multiply that by 100 again and said the answer was 7%. No, it is 0.7%. It's less than 1% of China's demand. Perhaps it's an unexpected answer, and that's why students did that. And question 11 is a 6-mark question, but it's one that requires a fair amount of data handling and quantitative analysis. We've been given a few bits of data here. We've got a graph that shows how much efficiency you would get from a wind turbine depending on how strong the wind is blowing. We've got a map showing 3 possible sites for a wind turbine: Kirkwall, way up in the Shetland Islands; Kinloss, up on the northern coast there; and Paisley, which is much further south, right next to Glasgow. It also gives us the location of Scotland's main 3 cities. We've got Glasgow next to Paisley there. We have Edinburgh, and I think that's Aberdeen up there as well. So it says that most people live in those 3 cities. Finally, it tells us what the wind is like in each of those 3 cities. We have winter and summer, so you can see Paisley has a much lower wind speed than Kinloss, and Kirkwall has the most. So another factor to consider is the distance from the wind farm to the consumers. Finally, it says use the data to compare the 3 sites for suitability as locations for a large wind farm. Essentially, in terms of marking this question, what the examiner was looking for was a weak candidate, 1 to 2 marks, probably has just talked about the distance. So said that Kirkwall is further away from the cities, therefore that's a problem, or therefore that's a good thing, whatever. A 3 to 4 mark answer will be looking for a student that has used the data in the graph in some way. A strong answer is going to be one that actually uses it quantitatively, and I'll show you what I mean by that. If we look at Paisley here, we can see that the average wind speed in the summer is 2.5 meters per second, and in the winter is 3.5 meters per second. Now, if we take a look at our graph here, you can see that 2.5 will be around about there, 3.5 a little bit further along, but in both cases, the wind speed is too low to have any electricity generated. That is below the minimum speed to produce any electricity from the wind turbine. So in that sense, Paisley is a useless choice, although it is close to the consumers. The flip side there is that Kirkwall and Kinloss do produce more, and Kirkwall, you see that they're at 8.5 meters per second. 8.5 meters per second would at least give you around about 40% efficiency. So it's not brilliant, but much better. So let's pull some of those thoughts together here in the answer. So Kirkwall, let's take them one at a time. Kirkwall, wind speed is 5.5 meters per second in the summer. And 8.5 meters per second in the winter. This would provide around 50% efficiency. However, it's remote, in other words, it's a long way from the cities. So there could be energy losses in transmission, in other words, in getting the electricity from one place to another, and maintenance could be expensive. Kirkwall. For Kinloss, the summer wind speed is 4 meters per second, below the minimum, so that will produce no electricity. And winter is 6 meters per second, so around 10% efficient. Finally, Paisley, as we said, so Kinloss is close to one city. And Paisley, as we said, close to cities, very close to one and quite close to another. However, wind speeds are too low for any generation. So it's not worth building a wind farm there. Finally, question 12 is about coal and nuclear power stations. It describes the amount of radioactive waste being produced by coal power stations and nuclear power stations. So the coal power stations produce ash that contains a little bit of radioactivity. For the same amount of energy produced by a nuclear power station, actually about 10 times less radioactive material is produced. However, that waste is mostly in rods as opposed to in the ash that's in the atmosphere. So maybe that's a good thing, maybe that's a bad thing. We'll discuss that in a second. However, it does say that it's more hazardous when it comes from a nuclear power station. So we need to discuss the problems associated with the waste produced in coal burning and nuclear power stations. Now, there's only 2 marks available here, and actually you don't need to say very much to get those 2 marks. Ionizing radiation is emitted from these sources. This can mutate cells and cause cancer. I think that would actually be enough for 2 marks right there. As I say, you don't need very much here. The coal produces more waste, but also produces CO2, which is a greenhouse gas. Nuclear produces less waste, but waste lasts longer, is more hazardous, and needs to be carefully disposed of. So this is a P3 question, not a P6 question. So the level of detail we're looking for related to radioactivity is not huge. Finally, we end with a calculation related to this. So it says that every megawatt hour of coal, 550 kilograms of CO2 are released. For burning gas, 180 kilograms are released. So a 1200 megawatt coal burning power station is replaced with a gas burning power station with the same output, 1200 megawatts. Calculate the reduction in carbon dioxide produced each day. Well, the first thing we need to work out here is the amount of energy produced in one day. So to do that, we need to multiply 1200 megawatts by 24 hours. And that will give us 28,800 megawatts hours. So that is the energy output of both of these power stations in one day. And calculate how much, excuse me, how much CO2 is released from the coal power station. So to do that, we multiply 28,800 by 550 kilograms, which is what the question tells us is released per megawatt hour of coal, which gives us 15,840,000 kilograms. And for the gas, we do the same calculation, 28,800, this time multiplying by 180, and that will give us 5,184,000 kilograms. So the difference between the two is what we're interested in. So that's 15,840,000 minus 5,184,000, and that will give us a difference of 10,656,000 kilograms of carbon dioxide every day. Okay, so that brings us to the end of this paper walkthrough. It's taken us almost exactly an hour, and obviously I've spent more time talking through and explaining things than doing in an exam hall. So you can see how this can be completed in an hour. I'm happy to take questions for a few minutes now before I log off. So if you want to, in the comments thread, I'll respond to any questions. Yeah, just to respond to a couple of questions here. In all of these questions, I've given you enough answer to get the full mark. So the 6 mark questions, there's enough detail there. In some cases, I would expect the 6 mark questions, you probably should be writing full prose. Remember, there was quality of written communication marks there. So where I've written brief notes, you should be fleshing that out. So with a 6 mark question, remember, look at the command words, look at the keywords in the question, jot down a few notes before you start writing. You have 1 minute per mark to answer this paper, but you can probably allow maybe 8 minutes for a 6 mark question, because there's plenty of marks in these papers that don't take you a full minute to get. For example, some of these, the tick box questions. Sam Crossley asks, can P waves travel through solids, or is that S waves? Both P waves and S waves can travel through solids. P waves can also travel through liquids. So P waves travel through solids and liquids. S waves only through solids. Somebody's just asking a question about how I got 50% efficiency. I know when I was circling on the graph, I circled around about 40% efficiency. But if you look at Kirkwall here, the winter wind speed is around just over 8.5 meters per second. If you were to look at 8.5 on the graph, it would probably be around about here. So we could read up there, and you see that would come out at 50% efficiency. That's where the 50%'s come from. I was just looking a bit more precisely when I wrote the 50%. There's a question there about volcanoes and earthquakes. You need to know what causes them in terms of tectonic plates, although I haven't seen many questions about that, to be honest. Modulated waves are not a topic in P1. You don't need to know about that. The rock cycle, again, doesn't come up a lot. If you have a look at my website, cowenphysics.com, I've put the specs on there, so you can see exactly what spec points you need to meet for each exam. Don't forget, they will throw in questions that are data handling, correlation, cause things, so you will see words that you've never come across in your life before. If that's the case, just keep calm, look at the question, and realize that quite often all of the information you need is on the page. I don't have any predictions, I'm afraid, because it's impossible to predict what comes up. You can see, looking back, that certain topics do come up time and time again. For example, the flow diagram I focused on related to the turbine, generator, and transformer. I've seen that a few times. Sankey diagrams didn't come up last year, but often come up. I would say look at each unit and kind of divide it into a couple of sections. The P1 broadly splits in half, or it splits into thirds. Really, you've got a section about Earth and space, which doesn't contain an awful lot of content, but you need to definitely look at the spec and see what you need to know. Definitely, I know it didn't come up in last year's paper, but it's definitely worth knowing parallax, brightness, and redshift as the 3 methods for determining the distance to a star. This isn't P7. You don't need to know them in detail, but you do need to know those methods and the limitations of those methods. 6 mark questions have come up about that before. The second part of P1 is to do with spreading, continental drift, tectonic plates, and so on. Vagueness stuff often comes up. You saw it come up last year. And in the third part is to do with waves and wave calculations. The P2, as I say, is mostly to do with the electromagnetic spectrum. Something that didn't come up last year but has come up in the past is digital. So that's using words like emit, transmit, reflect, absorb. So it can be quite a shock when you see a question that says you describe the journey of some light in terms of the standard model, but what it's really looking for is for you to say, for example, the sun emits the radiation. It is transmitted through the atmosphere or through a window. It's reflected off a book, and it's absorbed by our eyes. The other parts of P2 would be related to climate change, the greenhouse effect. Look at the greenhouse effect in a bit more detail. Okay, there's something that often gets, for top level answers related to the greenhouse effect, you need to be talking about the selective absorption and re-emission of radiation. That's when the Earth absorbs radiation and then re-emits it at a lower frequency. Have a look in your revision guides and textbooks to see that in a bit more detail. And the final part of P3 really would be related to digital and analog signals. We've been through a bit of that in the test today. And for P3, really you need to know the various methods of the various types of energy generation. So the renewable energy, wind, wave, tidal, solar, geothermal, hydroelectric, and so on. And you also need to know fossil fuels, gas, coal, oil, and biofuels as well, I suppose. So that's cutting down trees and burning them. And then nuclear power as well. You need to have a broad understanding of how each of these works in terms of fossil fuels being burned, nuclear power involving nuclear fission, and so on. But it's not P6. You don't need to know a lot of detail about that. And then also you've got the calculations involved in P3. You've got a formula sheet, refer to that. I think in terms of the maths questions, in some of those maths questions we've seen in this test tonight, but also certainly in one a few years ago related to waves on a pond. Some of you may have come across this question before. It was very, you didn't need to jump straight in and use any of the equations from the formula sheet. So look at the information you've got, slow yourself down a little bit and say, right, what does this tell me about the wave, for example? Does it tell me the amplitude? Does it tell me the wavelength? Does it tell me the frequency? And then from there, you can do any calculations if necessary. If you look on my YouTube channel, you'll see that I've gone through another P1, P2, P3 paper before. I'm not certain actually. There are some videos there about waves, and perhaps one or two other useful topics. The videos are probably more geared towards, or certainly A level, but there are some videos more related to P4 and P5 for when you get onto those topics as well after half term. Any more questions? The question from Samuel Crossley about doing a P456 paper. Probably not this year. I did do one last year that's available to watch back. I probably won't have time because I've got 3 more A-level papers to do this year as broadcasts. If I do, I'll put it on here. But as I say, you can look back when you come to P456 at the live stream I did last year. Shafak says that that's not true. P waves are transverse, S waves are longitudinal. No, which way around is it? P waves are longitudinal, S waves are transverse. Shafak isn't even a GCSE student. Go away and do some research. How and why a signal is transmitted as digital rather than analog? Well, if you look back at the question we did here, digital signals noise can be removed, and and you can also process the signals easily in a computer or store them in a computer. Okay, I'm going to log off now, but feel free to continue the conversation in the chat box, help each other, and good luck for tomorrow afternoon. Thank you very much for tuning in. So this video will be available basically forever on youtube.com/cowenphysics.